In this segment, I want to talk about frequency and period. Recall that in previous segment, we defined frequency as the number of complete oscillations per second, and we defined period as how long it takes for one complete oscillation. Let's investigate what determines the frequency and period for these two systems that we're going to study in this class, the pendulum and the spring, and the mass on a spring. Let's start with the mass on a spring. In the picture, again, I'm showing a mass on a spring that's moving side to side. Like I mentioned before, that's hard for me to model. We're going to do a mass on a spring oscillating up and down. The motion turns out to be identical. And there's some algebra in your textbook that demonstrates why it is that this motion is identical. I'm not going to go over it here. I encourage you to check it out if you're interested. So, what determines the frequency and the period? Well, here I have two systems. These are two masses on springs, and we'll just set them oscillating and see what we see. Okay, same period, right? Okay. What do you think would happen if I added an extra mass to one of these? So here we go. We're going to double the mass on this guy. Notice it stretches down a little bit farther. How do you think that will affect the period? Let's just see. Ooh, this one's definitely slower, isn't it? Right? So this one has a longer period and a lower frequency. Why? Because I added more mass to it. That's interesting. Okay, there they are. I've taken the mass off. Now they're oscillating the same. Here, I'm going to pull this one down significantly farther than this one. How do you think that's going to affect their period? Pulling this one down farther. There we go. Very similar still, right? So, the amplitude does not affect the period. Mass does, amplitude does not. How about the stiffness of the spring? Well, I've just got this one spring set up here. But it turns out, remember that the spring constant K describes how stiff or how hard it is to stretch the spring. You know, by just shortening this one, I can actually increase the spring constant. By making this shorter, I've made it a little bit harder to stretch. Let's see if that affects the period. Oh, it does. This one has a much shorter period and a much higher frequency now, doesn't it? Okay, so what affects the period of a mass on a spring? The spring constant, the mass on the spring. That's really it, right? What doesn't affect it, that's a little bit surprising, the amplitude. So here's the equation for the frequency of a mass on a spring. Notice it depends on the spring constant K and the mass m that I have attached to the spring. Notice here we've given the frequency and the period, but remember, the frequency and the period are just two different ways of describing the rate of wiggle, right? It's like, how quickly is it wiggling back and forth, right? That's what frequency and period describe in different ways, right? Period is time per cycle, and frequency is cycles per time. But they both tell us how fast they're wiggling. And remember, they are inverses of each other. And if you'll notice, if you were to flip this equation over, then you would get the period. All right, how about the pendulum? Here I have two pendulums. Let's see. Boy, same period. Pretty close, about as close as I can get in my basement here. Okay, same period there. What things could I do to change this system so that it had a different period? Here I have a longer string. What if I moved my mass to this longer string? How do you think that would affect the period and the frequency? Make a prediction. Think it would? Or do you think it would have no effect? Let's see. Okay, so with my string the same length, same mass, same amplitude, we have the same period. Let's see, if I put a longer string on, let's see what happens. Ooh, not the same anymore. Which one is swinging faster? Definitely this one, right? This one is definitely swinging faster than this one. So this one has a shorter period and a higher frequency. A longer string makes for a longer period and a lower frequency. Okay, now I've switched back to my same length of pendulums here, two pendulums of the same length, and pull them back the same here, and hopefully I'll convince you that they are dang close to the same frequency. Okay, now this time, I'm going to pull this one a tiny bit, and I'm going to pull this one quite a lot. What do you think? Think that'll affect the frequency in the period? Let's see. I think they're still swinging together, aren't they? Turns out the amplitude does not affect the frequency or the period. Similar to the mass on the spring. Kind of surprising, right? The amplitude does not affect it. I'm going to double the mass on this pendulum. Remember that with the mass on the spring, increasing the mass decreased the frequency and increased the period. How do you think this is going to affect this system? Let's see. Somewhat surprisingly, they still have the same period, don't they? I doubled the mass, yet it did not change the period. That is very surprising. Okay, so, again, surprisingly, the amplitude does not affect the period of a pendulum, nor does the mass that I attach to that pendulum. Here's our equations for the period and the frequency for a pendulum. Notice it depends only on the length of my string and the acceleration due to gravity. Obviously, I'm in my basement, and I'll have a very difficult time changing G, so I won't model that. You'll just have to take my word for it that if I did this experiment on the moon, where gravity is about 1/6 as strong, that we would have different frequencies and periods. In fact, if gravity was less, we can see that we would have a larger period and a lower frequency. Here is a quick example. The first astronauts to visit Mars are each allowed to take along some personal items to remind them of home. One astronaut takes along a grandfather clock, which on Earth has a pendulum that takes 1 second per swing, each swing corresponding to 1 tick of the clock. When the clock is set up on Mars, will it run fast or slow? The acceleration of gravity on Mars is 3.75 meters per second squared. Will it run slow, fast, or will it run at the same speed? Pause the video. I'll see you on the other side. So the thing to do here is to just look at the equation for the period here. So notice G is in the bottom here. It's under a square root, which complicates the math a little bit, but at the same time, it's on the bottom. So we see that a smaller G leads to a bigger T. In other words, the pendulum swings more slowly, and so the clock will run slow. Here's a numerical example. A 5 kilogram mass is suspended from a spring with a spring constant 200 newtons per meter. The mass is pulled down 10 centimeters and then released. How long will it take for the mass to return to its starting position, 10 centimeters below the equilibrium position? Okay, so here's a quick sketch. Hopefully you can see this okay. In yellow, I've sort of indicated where I pull this down to, and then I release it. Now, if it's just at rest, of course, this right here is our equilibrium position. So y equals 0 is where it would be if it was at rest and not moving at all. Again, equilibrium position, remember, means that the net force on the mass is 0. So I've pulled it down 10 centimeters and then I release it, which means that it will continue to oscillate from 10 centimeters below the equilibrium position to 10 centimeters above the equilibrium position. Recall that this point at which I've pulled it down to is called the turning point. That means that our amplitude is 10 centimeters. In standard units, of course, that's 0.1 meters. Now, it says that K, the spring constant, is 200 newtons per meter. So recall that that is K. So we've got K is 200, and M is, of course, 5 kilograms. Okay, so that's what we've got. Pull it down. How long does it take for the mass to return to its starting point? So we're going to pull it down, release it. It's going to go up and then back down. Is there a fancy physicsy name for that amount of time? There is. That amount of time is the period. Recall that the period is the amount of time for one complete cycle. If I'm going from the bottom up and then back to the bottom, that is one complete cycle. So I am looking for the period. Recall that we know that the period, the equation we have for the period, is 2 pi times the square root of m over k. And so once we've identified that we are looking for the period, this becomes a plug and chug. And now we just have to run our calculator. And we get an answer of about 1 second.